Thank you very much. It's always great to be at an AofA, and it's always so nice to talk about one of my favorite subjects, which are fringe subtrees in trees. And here specifically, I'm interested in distinct fringe subtrees. The presenter, however, is not working.
Click with the mouse, click on the slide once.
Okay. And now?
Doesn't work with somebody else's water.
No. I should have used this presenter. Okay. Good. Anyway, I think yesterday we learned what a fringe subtree is, but in case anybody forgot or came late, a fringe subtree is a subtree of a tree that consists of any of the vertices and everything that's below it. So in my example, the fringe subtree associated with vertex V2 is indicated by a rectangle. It contains V2 and all its children and also grandchildren. So you notice in this example perhaps that some of the fringe subtrees are of the same shape. For example, the fringe subtree at V2 and the fringe subtree at V6 are isomorphic as unlabeled plane trees, right? If I ignore the labels and just focus on what the shape of the tree is, then these are the same. In this particular example, there are in fact 5 equivalence classes of fringe subtrees. There is the one for the root, well, there's V3, that's the second largest fringe subtree in this tree. We've already seen that V2 and V6 give me isomorphic fringe subtrees. You have the cherries at V4, V7, and V10, and then all the singletons, all the leaves. So any tree with n vertices has automatically n fringe subtrees, one for each of the vertices, but many of them will be the same. So one might wonder how many of them are distinct, whatever distinct exactly means, but here I mean that distinct is they look different regarded as unlabeled plane trees, or the other way around, I consider fringe subtrees the same if they look the same as unlabeled plane trees. All right, now why would I be interested in the number of distinct fringe subtrees in a tree? One of the reasons is tree compression, and the best way I could think of to explain tree compression is with a cake, specifically this cake. I should explain. This is the cake that was used to celebrate Louisa Seelbach-Benkner's very successful PhD defense. And the cake features, well, tree compression, which is a main component of her thesis. So what you do there is you have a tree like this, and then you identify vertices that have identical fringe subtrees. So that is exactly what's happening here. The red vertices here, the 2 red vertices here have identical fringe subtrees, so they are merged. And also the green vertices have identical fringe subtrees, so they're merged. And what you get then is what is called the minimal DAG, directed acyclic graph, associated with the tree, which has fewer vertices, of course. And the number of vertices in this minimal DAG is precisely the number of distinct fringe subtrees in your tree. And this kind of tree compression, I'm told, plays a role in several contexts. Take my word for it. I read it somewhere. So tree compression is used in various contexts. Basically, you make trees more compact. That's the idea. And we would like to analyze how compact. So how much smaller do the trees get by compressing them to minimal DAGs in terms of the number of vertices? Now, there has been quite a bit of work on that. So as I said, measure a result for simply generated trees, it goes back to 1990, Flageolesi Pallastea in 1990, is that for simply generated families of trees with some additional technical assumptions, the compression is basically by a factor of square root log n. So there is a constant c involved here that depends on which specific family of trees you're considering, be it binary trees, labeled trees, plain trees, whatnot. In all these cases, so the expected size of the minimal DAG, or the expected number of distinct fringe subtrees, is constant times n divided by the square root of log n. And later, Luisa and I also proved this convergence in probability, which wasn't in the original paper. Right. So this is for simply generated families of trees, which include, for example, uniform binary trees. So to give you an idea of what this could be. So for uniformly random binary trees, the expected number of distinct fringe subtrees is 2 times n over square root pi times base 4 logarithm n. So that's the first order asymptotics. Right. So in this case, we have an order of magnitude of n over square root n. In today's talk, however, I will be mainly interested in binary search trees. So that's a slightly different random model than uniformly random binary trees. And we will see what's happening there. So in a binary search tree, the labels of the internal vertices follow a scheme where so all the numbers to the left are less than the root label, all the numbers to the right are greater than the root label, and that is helpful in searching. So left and right are separated. And we will be interested in what happens if you construct trees from random permutations in that way. It's also reasonably well known that this particularly random model is equivalent to what you get from binary increasing trees, where the labels are increasing from the root to the leaves, in the sense that the shapes of the trees that you get from the two random models are the same. So the probability measures on the shapes are the same. Right, to illustrate this, here is an example of such a binary search tree built from a given permutation. So you see that you've got the smaller labels to the left and the larger labels to the right of the root. Okay, so what do we know about binary search trees, and specifically the number of distinct fringe subtrees in binary search trees? Well, here there is first an upper bound due to Flageolet, Gourdon, and Conrado Martinez, who's sitting right there. The upper bound is of the order n over log n with a constant of 4 times log 2. And I've indicated this on the line here. So the constant for log 2 is 2.77 something. All right. Then there is a paper by Luc, who's sitting right here, giving a lower bound that's matching in terms of order of magnitude. It's also got n over log n, but with a different constant, you've got log 3 over 2. So, by the way, so his paper also contains a proof of the upper bound. So, but the two together tell you that the order of magnitude is n over log n. It's bounded between 2 multiples of n over log n, at least asymptotically. And then this was improved a little bit further. So Luisa and Markus Lorey, who's sitting up there, had a bound as sort of a corollary of a more general scheme of random tree models, where so if you plug into their result, you get for the specific case of binary search trees a constant of 0.6, a little bit more. And then we have one more update. As part of a different general scheme of things, as a special case there, we got a constant of 2.4 something. No greater than. I think it's greater than equal to, yeah. This is a lower bound as well. So we moved it over there. But of course, there is a gap there. So the expected number of distinct fringe subtrees is somewhere between these two. For practical applications, I assume that this makes hardly any difference whatsoever. So maybe the question is slightly academic, but the good thing if you work in academia is you're allowed to ask academic questions and get away with them. So what is the truth here? And I give you a moment to decide where you think the truth is on this red line. All right, drum roll. Here we go. It's at the left end. So the 2.40713 is in fact the right constant, as it turns out. And this constant is given by a certain sum. So it's 4 times log k over k plus 1, k plus 2. And this turns out to be the exact constant. It's both true in terms of expectation, and again, we also have convergence in probability. So if you divide by n over log n in probability, you converge to this mysterious constant 2.4, and so on. And I'll show you in a moment where this constant comes from. That's, again, the fault of somebody who is in the audience. But let's first talk about the binary search tree distribution. So I told you it's not uniform. And here is so the first instance where you see that it isn't uniform. It's all the possible trees with 3 internal and 4 external vertices. And in the binary search tree model, this one is slightly more likely. So it has a 1/3 as opposed to these that are all occurring with a probability of 1/6. And one can say exactly for any given shape what the probability is to occur. And it can be expressed as this product here. I take the product over all the internal vertices, and NV here is the number of internal vertices in the fringe subtree. Or if you just focus on the tree that's built from the internal vertices, it's the size of the fringe subtree rooted at V. So for example, in all of these, the product is 3 times 2 times 1 here in the denominator, so you get 1/6, whereas here it's 113 for a product of 3, and therefore a probability of 1/3. Well, that's a key ingredient, knowing specifically what the probability distribution is for binary search trees. And then you take the logarithm of this and get something that's called the shape functional. So negative logarithm, to be more precise. It's the sum of the logarithms of the fringe subtree sizes. And this has been studied. So specifically what we need is this result, due to Jim Phil from 1996. So if we take a random binary search tree of size n, so by size I mean external vertices here. There are various ways of defining size, but the formulas are nicest here if I let size be the number of external vertices. So if I do that, then this quantity has a linear expectation with logarithmic error term, and you already see this constant here popping up. It's pretty much the same as before, except that we have a 2 here rather than a 4. The variance is linear, and there is also a central limit theorem. We don't specifically need the central limit theorem for our purposes here, but it's mainly the fact that the quantity Ln here is concentrated that is relevant to us. So for that, the variance alone would be enough. But of course, it's good to know that it also follows the central limit theorem. All right, so these are the ingredients. And then I need a few things that are also reasonably well known about fringe subtrees of random binary search trees, specifically how many are there in total. So for any given size k, the number of fringe subtrees of that size k is in expectation 2n over k plus 1. And if you condition on the size of a specific fringe subtree, then it just behaves as a smaller random binary search tree. So if you take any subset of shapes that you might be interested in, and let pk be the probability that a random binary search tree of size k has a shape that's in that subset, then the expected number of fringe subtrees whose shape belongs to that set sk would just be expected total number times the probability that one of them is in sk. So that's something we need. And then this quantity is also concentrated around its mean. That's another important aspect of it. These are the ingredients that are required for the proof. And the proof is basically by distinguishing cases depending on the size of the fringe subtrees occurring in your tree. So you basically distinguish between large and small fringe subtrees. So for the lower bound, you focus on large trees, where large means at least, well, this mysterious constant 1/mu here. So mu was the mean constant in Jim's result. So that's the constant that you're using here. And you only focus on trees that are at least this large. And then for any k greater than or equal to this k naught, you choose a very specific subset of binary trees, sk, namely all those trees where the probability to occur, sort of as a random binary search tree, is bounded above by this quantity, and it's maybe more natural to rewrite it like this. So it's those trees where the quantity p of b is greater than or equal to the mean minus a little bit. And this a little bit is chosen in such a way that, in fact, most trees actually satisfy this, right? So we had a linear mean, but also linear variance. So standard deviation is root k. If you go down k to the 2/3, you're already beyond that. So you're basically already catching almost all trees that way. So that's the observation here. If I pick this specific subset of trees, sk, then with high probability, actually, a random binary search tree does satisfy this. So the pk that I had earlier, the probability that a random binary search tree belongs to sk is 1 minus a little bit. And then what you do is you show that most trees that belong to this sk can only occur at most once as a fringe subtree, and that holds with high probability for all of them. So that means they do not occur as duplicates. If they occur at all, they occur once somewhere in your tree. And the benefit of knowing that is that instead of counting distinct fringe subtrees, you can say, well, I'll count them all, because those that I care about with high probability only occur once anyway. So the number of fringe subtrees whose size is at least k naught gives me an asymptotic lower bound. That's what I mean by this greater than tilde. So this is a greater equal something that's asymptotically equal to this. And then this sum is easy. You get to n over k naught asymptotically, and by our choice of k naught, that's this. Right, so we've got a lower bound that's of this asymptotic form. Right, that's how you get the lower bound. That's something we already had before. So what I needed now was a matching upper bound. And there was just one trick that was really needed for this, and that's to also introduce a medium type of trees. So I split into small, medium, large. And again, for each type, I do something slightly different. So the small fringe subtrees are irrelevant because I bound them in a trivial way by the total number of possible binary trees that are that large. We know there is a Catalan number, so for each k, we know exactly how many possible shapes there could be. And even if they all occur, that's very few if I focus only on those up to this size k1. So those are estimated in a somewhat trivial way. The medium-sized fringe subtrees is where the more detailed analysis lies. So there it turns out that you can divide them further into two types, where there are those that have large shape functional. You remember that shape functional was negative logarithm probability. So large shape functional means low probability. These trees have low probability to occur as fringe subtrees, and somehow for that reason are irrelevant. Whereas those that occur with high probability somehow, there are simply not enough of those. All right, so you have those that occur, but there are not many of them, and a large number that have low probability of occurring. And turns out by sort of balancing these in the right way, you can prove that the medium-sized fringe subtrees also do not contribute asymptotically. And then the actual main contribution comes from the large fringe subtrees. And here you bound them again in a somewhat trivial way by just taking their total number and not caring at all whether they're distinct or not. Right, and that gives you the matching upper bound, leading to the final proof. I'll finish with a few remarks. So one remark you can make is that the constant here that was mysteriously popping up has something to do with an entropy, because you can interpret the expected value of the shape functional as the entropy of the shape of a random binary search tree, right? P of B is the probability that your random search tree has shape B. Now take the sum of P log PB, then that's, of course, expectation of the shape functional. So the growth constant of entropy is directly related to the growth constant for number of distinct fringe subtrees. And this is not exactly a coincidence. It works in other situations as well. So the method in and by itself, I only presented it for random binary search trees, but actually the method is reasonably general. So it does work for other types of random trees and also other ways of defining what distinct might mean, provided that you have information on the distribution of the number of fringe subtrees of a given size. So that was one of the key things that we needed. We knew exactly sort of what's the expected number of fringe subtrees of size k in a random binary search tree. And also we need information on the distribution of, well, an analog of the shape functional. So something that matches this. That depends on what you consider distinct, right? So here for us, distinct meant distinct as unlabeled plane trees. But you could also think, well, I don't want to distinguish between different ways of drawing them in the plane. If they're just isomorphic as rooted trees, that's good enough for me to count as the same. You could do the entire analysis with that notion as well. So as I said, what you need for that is to have some analog of the shape functional and a similar concentration property. So I hope to show this in a number of examples in the full version of the conference paper. That's it for me. So thank you very much for your attention.
Are there questions?
Yes.
I'll do Wojtek first because he's on the way.
Ah, it's closer, yeah.
So there is much more work on the compression of trees. I'm just reviewing the papers I've forgotten. So first, your mu is actually entropy of a tree. You can compute it.
Yes.
Second, the compression is related to non-plane trees. And actually, Bona and Flageolet wrote a beautiful paper about it. But for a kind of uniform model, for non-uniform model, we did something. So there is, in order to compute entropy, you have to actually compute sum of p-square probabilities. Mm-hmm. And Huang and Martinez had a beautiful paper where it was published with very interesting analysis. But for binary case, extension to non-binary is very difficult, as I understand. Maybe they can come and let me tell you what it is. So this is Chen, Huang and Martinez psi series method for equality of random trees and quadratic condition, and this is random structures.
Yep.
So
Yeah,
I think there is much more work on.
I know that. I know that particular paper. Also, I think I know the one that you meant. Is that with Kiefer, perhaps?
Sorry?
Yeah, the paper of yourself that you mentioned, is that the one with Kiefer, maybe?
Transaction information theory and another in town.
Yeah. I think I know these one as well. So there is indeed a lot more. There are a lot more models. There are a lot more notions of distinctness you can study. There's plenty more out there. Yes. This is just sort of one case of tree compression, and one particular model where I'm giving the precise analysis.
My question is there any hope of pushing this even further to get non-degenerate limiting distribution for?
Yes, it's a very natural question. As far as I know, not even in the simply generated case where the convergence in probability or the expectation with precise constant was known before, there is a proof of a limit distribution. I don't even want to guess what it might be. Perhaps Gaussian, but perhaps not. So maybe, but certainly in this particular case, I don't know how to approach it. Maybe in the simply generated case where I told you it has been known, the precise constant has been known for a much longer amount of time. There is more hope, but even there, as far as I remember, it's not known, it hasn't been studied.
Oh, okay, so to not on the comment, I would say my guess is that there's simply a good chance that it actually might be Gaussian, since I think if I understood you right, most of these trees, you would see different ones will be rather large and occur with rather low frequency. So you have a small probability for each one of them, and they will be more or less independent in different places. So it's a situation that looks as it could be Gaussian. But I was going to ask you a more concrete thing. I guess that it follows from your methods here. How big are the typical fringe trees? I mean, if you just, which size dominates the count of different types?
Well, the large ones. So
yes, how large? Will it be, I guess it will be some constant or times log n, but...
so if we look back where we distinguished, so both in the proof of the upper and the proof of the lower bound, you notice that we were cutting essentially at
1 over mu. Yeah.
At this 1 over mu times log n. And from there onwards, the trees matter. So that's basically it. So so here, this is sort of the sum that gives you the main term, and that comes from the trees being greater than or equal to 1 over mu log n, give or take. So that's where the main contribution comes from.
Okay.
And that's exactly why, as you say, there may also be hope to prove a limit theorem, because if you can make this so precise that you show that the others really don't matter even for the limit distribution, then it would follow. The problem is, I think that the estimates for the rest are too weak. So the estimates are not good enough to sort of be negligible compared to the standard deviation of what comes from here.
Okay, thanks.